Okay, so the next thing we're going to look at in our whole idea of linear models, and you've seen this in hopefully first year and second year, but let's really sort of nail it down, is assumption checking. So what do we mean by assumption checking? Well, if you think about it, I keep going, my model is this, and then we go and fit it to the data. And what we're saying is, our assumption is that that model's a good model, and there's various things we talk about in that model. And then assumption checking is going, the simple fact of, is that a good model for this data? Because if it's not, then I need a better model. As simple as that. And as we go on this course, we'll sort of talk about, well, when my model's not good enough, how do I adjust it? But that's the key idea is, when I write down a model, and it's where I've got to be really precise with my mathematics, I'm making a statement about what I think the truth is, and then I need to check it's right. So let's think about our linear regression. So we've got y equals x beta plus epsilon. And our epsilon are I.D. normal with a mean of 0 and a variance of sigma squared. So the question is, what are all the assumptions I've made writing that down? Well, here they are. First of all, I said that all the EI, which are random variables, have a mean of 0. All the EI have the same variance, sigma squared. All the EI are normally distributed and they're independent. You go, wait a minute, where's the independent? Remember the bit where I go IID and I say it really fast and you ignore me? One of those I's means independent. You might go, well, why do I make assumptions like that? Well, if you remember all your derivation of the results, it makes the maths easier. I don't have to have them IID. I could have some sort of dependency structure. But once I do, the maths gets harder. So it's a compromise. You can have extra assumptions, maths gets simple, less assumptions, maths gets harder. Simple as that. In addition, we're also going to assume that the x variables are known without error. So we've never really talked about this in your courses, but basically I'm saying my predictors are known and there's no error in them. You can actually have these more complicated models where you have basically your x variables, instead of being sort of fixed constants, are error terms as well. And the other thing is that the errors EI are not correlated with the x variables. There's no relationship with them as well. That is, for example, your measurement error, in this case, your EI doesn't depend on the value of your predictor. So what do we normally do? Well, the first three, assumptions 1, 2, and 3, are what we call model assumptions. There's usually a plot. There's something you can do. You can look at the data and go, are these reasonable? The others 4, 5, and 6 are what we call design assumptions. There's not really a good plot you can do. What you do instead is you go and look at how the experiment data was obtained, hence design. How was it designed? So how do we test a lot of these things? I said the first three we can test where we use what we call a residual. What is a residual? If you think about residual in common English, it's the stuff that's left over. And that's what it is to some extent. What we've done is we've got a model and we've fitted it, and we take it off our observations. So that's the stuff that's left over, hence residual, which we denote as that. I mean, you think it in mathematical terms and just go, oh, well, it's the observed minus the fitted. But it's the stuff that's left over once I remove my model. Here's exactly the same thing in vector notation. So we just go y minus x beta hat. And I'm calling them ordinary residuals because we're going to get two more in a second. Well, why do we do that? Why do we go observed minus fitted and have a look at it? Well, if you think about it, in our model, the e's are independent, identical, normal, 0, sigma squared. But I don't have the actual true e's. What I do is I have the next best thing, which is what I've got from my observed data, which is the EI hat, which is the y minus the, well, ideally I want y minus x beta. I don't have beta, so I have y minus x beta hat. So they're sort of like a good plug-in substitute for the true value of this e. And roughly what we should get is, hopefully, our things we just calculated from the data, our EI hat, are approximately equal to EI. So we know that the EI should be normal 0 sigma squared. So hopefully our EI hat should be approximately normal 0 sigma squared. Not quite though. Because if we actually think about exactly what the distribution of these residuals we calculate, so our E hat. So E hat is y minus x beta hat. So you've got this sort of noise estimate in there, which we can write as I minus hy, where h is our projection matrix is x transpose x to the minus 1 x transpose. So we can derive the expected value in the variance. Well, the expected value of EI is 0, so that's good. Our new random variables, which we get from the data, they have an expected value of 0, which is what we wanted, because the true expected value of E is 0, so that's good. What about the variance? Well, that's the variance of I minus HY. We rearrange that. This is a constant, it comes out the front. Variance Y, I minus H transposed. The variance of Y is just sigma squared I. So I get sigma squared. So it's almost sigma squared, but not quite. You've got this problem, this extra term. And the problem with that is this matrix, first of all, probably doesn't have zeros on the off diagonals. So there's going to be some covariance, so some dependence between our observed residuals. And also the variance along, which is the diagonal, that's also not going to be all the same. In fact, the variance of the ith observed residual is sigma squared 1 minus HII, where HII is the ith element of your diagonal. Let's just have a quick example. Imagine this is my design matrix. I've got something very simple. I've got a single predictor which has values 1, 3, 5, and 7. And here's my intercept. If I now calculate my h with my usual, so this is x transpose to the minus 1 tx, and I get this is my h. And so my 1 minus my diagonal means you're going to get this adjustment. So basically the two in the middle are going to be about 0.7 of sigma squared, and these are going to be about 0.3 of sigma squared. So we've got a problem there. So the first thing we do is we're going to invent a new, we're going to introduce a new residual called a standardized residuals. And I'm going to denote this by EI dash. Basically, I take my residual and I adjust by standard error. So I know that as you get further out from your data, you're going to get a change in the variance, and we need to adjust for this because of what we call the leverage. We'll introduce that in the next lecture, but I'm going to adjust for it. So that's what I've done. So now what I've done with my standardized, by standardizing them, they all have equal variance. But that hasn't done anything with the off terms. There still could be a problem with some sort of covariance structure. The other problem is, imagine I have a really bad Y value, and we'll talk a lot about this in the next topic video. And what that's doing is, if you can think about your straight line, maybe it's sort of pulling that line in the wrong direction. And because of that, because it's sort of poisoning your model and dragging it in the wrong direction, it will change all your residuals. And it might be that that point should have a remarkable residual, but because everything's dragged towards it, you don't pick it up. So the fact is, certain points can basically break your model. And you can't necessarily pick it up because the thing we're using to pick it up is the model, but the model's broken, so you don't pick it up. So what do? We have a new one called a studentized residual. What's a studentized residual? Basically, it's y minus the fitted divided by the square root, so the standard deviation of y minus the fitted, but not quite. Notice this I here and this I here. What we're doing is we are working out the residuals and standardizing it by using a model that has all the data except for that point. So if you had that poison point, you would fit it to all the rest of the data. The model would now say, oh, that really sticks out, because when I don't look at that point and I look at the rest, it's got a huge residual. So the studentized residual is basically going, here's the residual you would get if we used every other observation but this one to fit the model. Make sense? You can show there's a relationship between them, between the standardized and the studentized. It's here. So what we're going to do with this? Well, studentized is probably the best one to use if you can. And ideally what you should do, you should use the studentized and plot it against the fitted. The next thing you should do is you should also plot it against each predictor. Now, if you have a single predictor, the fit and the predictor are exactly the same. You don't have to do that. But if you have multiple predictors, you shouldn't just do residual versus fitted. You should do residual versus predictor 1, residual versus predictor 2. Because occasionally you can find the residual versus fitted looks fine, but once you look at individual predictor, you find a pattern. The other thing you should do, if there's any extra stuff like time when you measured that, stuff like that, the other thing you should do is do a residual against time to look for a trend. As I said last time, and I've mentioned in a couple of things, when you have independence, a couple of things that can cause dependence are things like clustering, time and space. So if you have something like time, in this case, plot it against that. If you've done all that, if you've done all your residual versus fitted, residual versus predictive, residual versus time, and it's all looking good, then you can now do a normal quantile plot of your residuals. Okay. I will actually go through an example of doing all that in a case study for this week, so don't worry about it. So next time we'll look at inference diagnostics. See you next time.